Okay, so hi everyone, I'm Ming-Feng from UC Riverside. It's actually my first time doing virtual conference, streaming online. So hi Mom, I'm here. So I'm going to present finding strong Lyman alpha absorbers in the shadows of quasars with Bayesian machine learning. And this is the paper we submitted at March and done jointly by me, my PI Simeon, and computer scientist Romain in St. Louis. What do I mean strong Lyman alpha absorbers? I mean DLAs. So they are usually dense hydrogen cloud around galaxies. So when the light emitted by quasar runs through those dense gases, Lyman alpha photons would get absorbed and leave a wide absorption feature with damping winds in a spectroscopy survey. So as you can see, here is a DOA. So they are usually found between redshift 2 to 5 and dominate the neutral hydrogen budget after reionization. And what do I mean Bayesian machine learning? Basically, we developed a probabilistic pipeline based on Gaussian processes and Bayesian statistics. And in the end of the talk, I will also talk about our new paper on how we extend our Gaussian process model to do quasar redshift inference simultaneously. So what are the Lyman alpha absorbers and why they are important? DLAs are neutral hydrogen gases around galaxies with very high current density. The convention is larger than 10 to the 20.3 inverse square centimeters considered to be DLAs. And in the cosmological context, because Lyman alpha forest is a tool to build power spectrum, and DOAs usually are considered to be systematics will bias the estimate of BAO. So if we want to do BAO Baryonic acoustic oscillation analysis out of the spectrum produced by Lyman alpha forest, you need to remove DOA first. Another point, DOA, because they are gases around galaxies, DOAs will eventually fall into galactic halos and fuel star formation. The abundance of DOAs as a function of redshifts will give hints about the galaxy formation. The final point is that since the hydrogen is the major component of the baryonic matter, DOAs also give some hints about total baryonic matter in the universe. But why finding DOAs is a problem? So the problem actually is finding DOAs now is done by visually expecting quasar spectra with a bunch of trained astronomers. For example, this is a quasar spectrum with the rightmost peak to be the Lyman alpha emission peak at 1216 angstrom. Those little wiggles caused by Lyman alpha, weak Lyman alpha absorbers in the forest. But what we want is to find a bigger and denser Lyman alpha absorbers like DLAs. The state of our method, however, is asking trained astronomers to fit the DLA profile to the spectrum by their eyes. And by trained astronomers, I mean graduate students, But in the future, we will have millions or billions of quasar spectra. This means we won't have enough money or grants to pay students to do visual inspection in the future. So what we can do is to automate the detecting pipeline with machine learning. Oh, and we also need to take care of students' mental health, especially during the pandemic, right? We can do better than just treating students like data points. So we can develop automate the procedure finding DLAs to allow those poor students to be released from those labor-intense works. So why we need machine learning? Obviously, first of all, is because the state of art is GSN, graduate student method, and this method is not scalable to a future survey like DESI's dark energy spectroscopy instrument, which we will have millions of spectra. This makes visual inspection impractical. Second reason was there's no physical model for quasar emission. There's no generalized physical model for quasar emission, and the only thing we can rely on are the statistical properties from the quasar observations, and also distinguishing between those little wiggles weak absorbers from the forest and the strong absorbers like DLA. It's not trivial. It is very easy to mess up between identifying a bunch of weak absorbers and a strong DLA. So what we do is to learn the quasar emission model using Gaussian process and encode the Lyman forest model into the Gaussian process. So let's briefly talk about what is Gaussian process. What is a Gaussian process? A Gaussian process is a way to do Bayesian function interpolation. If we have some data points sampled from an unknown function, we can use Gaussian process to interpolate the data points and predict the underlying function. The Gaussian process will be a probability density function describing the unknown function. The left panel is the Gaussian process prior we place on the function. If we get some data, we can condition our prior on the data and get posterior like the right panel. Another important component of GP is the kernel function. The kernel function describes how different points correlate with each other depending on the parameter distance. Instead of using a predefined kernel, we actually trained a Taylor kernel function from SDSS DR9 quasar spectra. This kernel will describe covariance between different emission lines in the quasar spectrum. So in the end, we will have a GP prior function trained from data, describe the quasar emission function, and we can condition the GP prior on new data and get the posterior probability that how well the GP can describe the new data. Our method depends fully on Bayesian model selection framework. The trick we used is to first train a GP prior for QSO emission without any DLAs, and we built another GP prior for quasar spectrum having DLAs. So each GP prior can serve as a likelihood function. Now we can use these likelihood functions to see how well the new data we get from an object could be explained by each GP pair. And since we are Bayesians, we can put model pairs on each likelihood function, and we learn our model pairs also from the training data. In the end, we will have model posteriors describing how likely a given model could be explained by a given quasar spectrum. So here I schematically describe how Bayesian model selection works. In the top panel here, top panel, the dashed red curve is the GP mean prior before adding Fourier suppression. The null model without any DLAs is in the solid curve. The Lyman Fourier will effectively suppress the observed flux to a lower level. We model it as the suppression of the GP mean prior. Once we have our GP null model in the solid red curve, we can calculate how likely this spectrum can be explained by the null model, and we can get the log probability on the right hand side, which is negative 1030. Right hand side 1030. And we can also calculate the probability of this spectrum explained by one DLA inside the modeling window, and so this one is in the middle panel, and the log probability is here, negative 811, and so on and so forth. We can calculate 2 DLAs in the modeling window and 3 DLAs in the modeling window. And finally, we need to select the one with the highest probability. For this one, we select the one DLA model, and we can furthermore calculate the model posterior. In this case, the model posterior is 0.989, having one DLA. But how do we calculate the probability of having DLAs in the spectrum? What we do is to sample all possible DLAs within a prior volume of the parameter space and marginalize the parameters to get the probability of having DLAs. So here the plots show you the prior volume in the parameter space. We have here the x-axis is the redshifts of the DLA. The y-axis is the log column density of DLAs, and the color shows the probability, and the yellow color here shows that we have very high probability to have DLA here, and we can interpret it in the spectrum. It looks like this. The maximum a posteriori estimate is in the bottom panel, and since we model the Lyman beta and Lyman gamma absorptions of the DLA, we won't mistakenly predict land as another DLAs. Here we show the ROC curve, which we validated our method on SDS DR9. The orange curve shows our paper at 2020, and the blue curve shows the curve of our original paper in 2017. As you can see, the current revised version has a better AUC score. An AUC score is the area under the curve, which can be interpreted as the accuracy of the model predictions. And as you can see in the middle part of the curve, our current model is closer to the upper left corner. This means we can have a better handles of our sub-DLAs. with our current model. So we can furthermore propagate our probabilistic estimation of DLAs to the current density statistics. This is the current density distribution function, which is the number of DLAs per unit absorption length per unit current density bin. Basically, CDDF, the current density distribution function, shows the abundance of DLAs as a function of current densities. You can see we basically reproduce the measurements from previous dataset from Notre Dame, and since we propagate the uncertainty instead of setting a hard threshold on DLA posterior, you can use all of the data, even those with very low signal noise ratio. The result is that we will have a larger dataset to make the measurement. Here we show another CDDF from another machine learning model reported in Parks et al. 2018, and they used a CNN model, the convolutional neural network model, to find DLAs. That the paper was actually very interesting, and their method was very robust on finding DLAs with accuracy of 0.98 probability. But the current density measurements of the CNN model was not actually very accurate at the high end comparing to our measurement. As you can see, there's an offset there comparing to Notre Dame 12. And so this is another important statistics of DLAs, the total mass of DLA. This plot shows the total hydrogen mass content in DLAs in the units of cosmic density as a function of redshifts. Again, our measurement is consistent with others, and since we count all of the weak detections, so we are able to extend our measurement to redshift larger than 4. But we didn't know that most of the detections for Z more than 4 are just detection with very low posterior. So the error bars are very large. But overall, we can say we detect moderate increase of omega DLA over the range of 2 to 4. So this is the bonus page on our recent submitted paper in June. This is work jointly done with CS people in UC Riverside, including Lee, Christian, and Ishita. What we did is using our null GP prior to make inference on quasar redshifts. As the video shows, we can ship the data with ZQSO as a free parameter, and we can calculate the GP likelihood to find the maximum a posteriori estimate of ZQSO. To do this, we need to extend our model to magnesium 2 line, which result in a very large kernel function on the right hand side. And the kernel function shows clearly the correlation features between different emission lines in the quasar spectrum. And with our new GP model, we can achieve 99% accuracy on finding the redshifts of quasars in the end. And I will just leave the conclusion slide here, and you can find the link to our paper on this page, and our model and our codes are probably available also in this conclusion slide. Thank you very much. Close the recording.